And let's move on to the next talk, which is by Professor Deepak Dhar from IISc Pune. And he is going to, the talk title is the phase transition from the nematic to high density disordered phase for long rods on a lattice. Professor Dhar, are you there? Yes. Can you make it full screen?
Yeah, click on the view.
Yes. We don't hear you.
Sorry.
Yes, yes.
Now?
Yes. Okay, yes, yes. Over to you. Yeah.
So let me start by thanking everybody who has come to this meeting. Okay, start now. So, you know, when I was very young, I had read some place that if there is a problem on which you work for a very long time, it becomes interesting. So this is one of those problems which I have been working on for a long time. But I thought it will be interesting even for others, and that is why I want to discuss it with you briefly here. So this work is done with Agam Shah, who is a student or was a student at ISR, and with Rajesh. And so it is dealing with hard rods and phase transitions in hard rods. And let me give you the outline. So the problem of hard rods has been studied a lot. I will discuss the earlier studies, and then I will mention the fact that there are two phase transitions in hard rods. This was done with Anand Mohan long time ago. And then we will tell about the recent results on hard rods, precise statements, and try to explain how this happens. Okay, so Onsagar in 1949 was the first one who had this pioneering work on long needle-shaped rods in solution and showed that they undergo nematic order if the density of rods is high enough. Then we are going to study lattice models of hard rods. So on a lattice, you have long needles with thick width 1 and length k. And you can have it in 2 or more dimensions. And then you study what the only interaction is the excluded volume interaction. And we want to see what happens as a function of density. Okay, so this was, I already mentioned, but anyway, here is a picture. And so with Ghosh, we had shown earlier that this model actually undergoes two phase transitions, one from the disordered phase to a nematic phase. But if the density becomes high enough, then the nematic order is lost and you get a different type of disordered phase. So in this picture, you see 2D rods with length 7, and the density in this first part is 0.66. Then there is equal densities of horizontal and vertical rods. In the middle one, it's mostly nematic. And if you go to high enough density, again, you get roughly equal number of horizontal and vertical rods. So this first transition from this nematic to the, from the disordered to nematic state has been studied a long time. This was, of course, studied first by Onsagar, but this is on a lattice. And on the lattice, it is known that it is in the Ising universality class in 2 dimensions. The second transition has been less studied, and there are some earlier works, but they are not very conclusive, and they give different kind of answers. So we will not discuss them in great detail here. So let me just give you a summary of what I would like to describe to you here. So we have non-rigorous arguments, perturbative based, but the claim is that for all hypercubical lattices in all dimensions for large scale limit, the second transition is a first order transition. So if you have a first order transition, you would like to know at what chemical potential does it occur and what are the values of from what density to what density is the jump in the density. And these are the conjectures. They are not fully established, but they are we give some arguments for these. So epsilon 1 is the density of holes at the left of the transition. And, so for large K, this goes like 1 by K squared in this particular way. The chemical potential mu star also has some dependence, which can be written like this. And the second density of holes on the right of the transition is epsilon 2 of k. And that has this behavior, that its ratio to epsilon 1k is very small. Okay, or more simply, it says epsilon 1 of k goes like log k by k squared, mu star goes like k log k by log k, and epsilon 2k goes faster than k by m. And interestingly, this coefficient of log k by k is always 1 in all dimensions. And even for mu star, the coefficient is 1 in all dimensions. So this is the conjecture. Now I will give you the support for this conjecture. So for perfectly aligned rods, the problem reduces to one-dimensional problem. And one can easily get the expression for entropy as a function of density of holes epsilon. So there is a formula which you can easily derive. But it turns out that for long rods, this approximation is actually very good. And if you work at a finite epsilon, the fraction of rods which are not of the majority type is very small. And in fact, if the density of holes is epsilon, the correction to the entropy and the fraction of the opposite type rods goes like epsilon to the power k when epsilon is small. So here there is a plot of the correction to entropy as a function of k. And for k equal to 7, 12, 14, but the numbers are like 10 to the power minus 7, minus 14. So the correction to entropy is very small, and this formula is very good for most epsilon. However, if you go to epsilon tending to 0, it develops divergence and it doesn't work. Okay, so then the second part in the argument is that at full packing, the Kmel problem on the lattice has a finite entropy per site, which goes as log k by k squared with coefficient 1. But this nematic entropy, which we said is very good and works up to 10 to the power minus 14, 15 or whatever, tends to 0 as epsilon tends to 0. So it cannot be right for all values of epsilon. And so here there is a S of epsilon curve, which is S nematic. And this one is the finite entropy at S equal to 0. And then there is a tangent construction, which is convex envelope construction, which supersedes the nematic. And so for small epsilon, the entropy is higher for a phase separated state. So suppose the density of holes is somewhere here in this interval. Then it is better for the system to phase separate into one region which has no holes and one region which has a density epsilon 1. And then you get a higher entropy, which is the tangent curve and not the black curve. Okay, so now given we have an approximate value of the intercept, which is log k by k squared, and we have the S entropy. So it's straightforward to calculate the tangent and hence calculate epsilon 1 and epsilon 2 and the mu star, and these are the values you get. Okay. So now comes the important point that these results do not change to leading order if presence of holes in the dense phase is taken into account approximately. So we consider an approximation to the dense phase, so we consider tiles which look like this, and you can make a long strip of length k by joining these tiles at random, and then make a 2D lattice by joining strips of such types. But the advantage of this construction is that you can calculate the partition function exactly when you have this restricted set of configurations over which you work. But the point is that this approximation gives the correct asymptotic density of entropy density at full packing and allows the exact calculation of partition function. And when you do this calculation with holes, it turns out that epsilon 2 is very small. So the old calculation which we did doesn't change much. and the leading behavior of epsilon 1 and mu star is unchanged. So then we did a little bit more, which is an elaboration of the previous one. So you don't allow only 3 types of tiles, but you allow all possible structures within a strip of length k. So there you have vertical rods which are separated by horizontal intervals of horizontal rods. And so one interval in which there are no vertical rods is called an irreducible segment. And you can work with these irreducible segment. They have some partition function. Then partition function of the whole thing can be expressed as a geometric series of this stuff. And then we can calculate the full partition function if you can calculate the partition function of one segment. But the partition function of one segment is easy because, there are only horizontal rods. So it looks like some one-dimensional partition function to the power k. And so we sum this series numerically. We cannot do it analytically, but determine x star using the condition that are in this sum of partition functions is 1, and calculate the density, and you find that the density of holes as a function of chemical potential has the following behavior for different k. So you see sort of a jump in the behavior. It is not a strict jump in one dimension, but it's slightly rounded off. But at the scale in which it is drawn, it looks like a jump. And so, well, this is the summary. So these results can be extended to higher dimensions, because suppose you work in 3 dimensions, then it turns out that the most efficient way to do packing of rods in 3D is to break them into layers, and in each 2-dimensional layer you pack it as a 2D configuration, and then different layers can be packed independently. Otherwise, if you put vertical in 3D, if there are horizontal plane and vertical rods, then the vertical rods cause too much of difficulty in packing the others. So we have argued that in the large scale limit, the nematic to disordered phase transition on a d-dimensional lattice is the first order transition. We give the leading behavior of the chemical potential and density jump. The recent Monte Carlo evidence shows 2-phase coexistence, which is sort of another signal of the first order phase transition. The arguments we gave were not rigorous, they were perturbative, but we expect the conclusions to be true. And it will be nice if, so it's very intriguing because you see the coefficients were exactly determined, and they are these simple numbers 1 for all dimensions. And it will be nice if one can have a more rigorous derivation of these results. So that is where I stop. Thank you.
Thank you, Professor Dhar. If there are any questions? Yes, Tridib, go ahead.
Yes, hi Deepak. So you had the 2 different disordered phases in the 2 different densities. One is the low density and the high densities.
Yes.
Now these 2 phases, do they differ in certain characteristics? And my question is related to the 2-step melting scenario of disks, where you have another different order parameters, which is orientation order parameter, which would separate 3 different kind of phases. Is there any such analog for the 2 different disordered phases that you see at extreme 2 densities?
We have looked for it and not found one yet. But there is a feeling which I have had but haven't been able to show, is that the disordered phase in the high density has power law correlations, while the disordered phase in the low density has exponential correlations. But that's a guess.
In the orientational order?
Whatever order, whatever variables you look at, exponentially correlated phase is, sort of disordered. And the high density phase will be power law ordered in many variables, not necessarily in every variable, but in many.
Deepak, including in translation variables, right? Even for k bigger than 7.
I haven't studied this very well, so I don't know the answer, but I would guess yes.
Okay.
And the fact that there is still a power law dependence in the disordered state, and still the transition between the ordered and the power law phase, it still remains a first order and not a KT type or any such analog.
Yeah, that is what we find.
Okay. Okay. Thanks.
Okay, Dibendu?
Yeah, so just little curious about your last comment that in the fully packed limit, of course, there is a power law correlation. Now you are telling that just in the high density phase also possibly there is a power law correlation. Do you sort of hope these are the same kind of power laws, or you are thinking that it might be different, or any such thoughts are there?
I really don't know, so I will skip this one. I don't know if it is the same power.
Oh, okay, fine.
Shoham?
Sorry, I had a similar question in a different language. Like
We
a
can't
similar
hear
question
you.
in different languages, Dubendra, but I do not have that question right now.
Okay. Okay, if there are no other questions, let's thank Professor Dhar once again